Okay, so today we're going to talk about equations and inequalities. So equations use the equal sign, right? So this could be like 5 times 2 equals 10, 7 times 4 equals 28, 7x equals 28, right? All of these are using the equal sign, so these are equations, right? And over here we have the left side of the equation, right? More often than not, this can be referred to as left-hand side. Over here we have the right side, or similarly, right-hand side. Okay, and an inequality just uses inequality symbols, right? So this could be like greater than or equal, less than or equal, or not equal, right? So some examples of this would be like 3 is less than 8, 9 is greater than 4, 6 plus 7 is less than or equal to 18, 48 divided by 16 does not equal 4, okay? And again, these things on this side of my expression, this side of my expression are the left-hand side, and over here we have the right-hand side. Okay. If there are numbers only in the expression, then the expression is either true or false. Right? I could write down any expression that I want. So maybe I write 5 plus 9 equals 14. This happens to be true. Maybe I write 7 is less than 9, also true. 6 does not equal 40 divided by 8, also true. 12 is greater than or equal to 12. That's also true. Or maybe instead I write 5 plus 10 equals 14, right? I can write whatever I want. Just because I write it doesn't mean that it's true. So this is false. I could have written 7 is greater than 9. That's also false. Or 5 does not equal 40 divided by 8. Okay. Now, I want to take a moment to talk about the set of numbers that can satisfy an inequality versus an equality. Okay, so let's say that I'm looking for the set of integers such that, so when I put this st, that really means such that the following are true, okay? I would like the set of numbers such that 12 is greater than or equal to x. And independently, I'd like the set of numbers such that 12 equals x. Okay? And x is an integer, so we say x is in z. Now I know before, in an earlier section of your book, they used j to represent integer. That's not as widely used. In most cases that I've seen, z is the letter that represents integers. So I'm just gonna say these are integers. Okay, so that's the domain for x, it's integers, and I would like the set of numbers, the set of values for x that satisfy these two expressions. Well, over here on the right, 12 equals x can only be satisfied for x equals 12, right? So that means my solution set here is going to be x is in the set 12. On the left, the things that satisfy this are going to be 12, right? 12 is greater than or equal to 12. This is a not very well written curly brace. There we go. 12. 11 is going to satisfy that, right? 12 is greater than or equal to 11. 10 will satisfy it. 12 is greater than or equal to 10. And we can kind of just go down the line, right? So it's going to be all integers smaller than 13. Now, let's say that my expression had been 12 greater than x instead of equal to x. Then my solution set would be 11, 10, 9, right? 12 no longer satisfies that expression, okay? So the major takeaway here is that my solution set for an inequality is often going to be much bigger than my solution set for an equality. Oops. Inequalities tend to have bigger, as in more numbers, bigger solution sets. Okay. Now, these expressions that we've been talking about are called mathematical sentences, right? So that is, a mathematical sentence is an expression with an equality or an inequality, right? That kind of makes sense because when we read these expressions, it kind of comes out like a sentence, right? 12 is greater than or equal to x could be written as the sentence 12 is greater than or equal to x, right? Now, when we have variables in the sentence, such as, 2x minus 5 equals 35, or a is greater than 11, or 24 does not equal n divided by 3, right? All of these have variables. You have x, a, n. So when we have variables in the sentence, this is referred to as an open mathematical sentence or an open sentence. Okay? And for these open sentences, the variables in the sentence will have a domain. So there's a domain on variables in open sentences. What this means, what the domain means, is the set of values that the variable can be, right? So for example, if I took a look at a is greater than 11, I could have various domains on a. I could have, well, a can only be in the set 10, 15, 20, 25. Or I could say a can only be an integer. Remember that z is integer. Or maybe I say a can only be a positive integer. Maybe a can only be in the set 0. Okay? And once I specify the domain, then there's going to be a subset of the domain where when the variable is in that subset, it satisfies the expression. Okay? So let's make a note of that. Once domain specified, there will be a subset of the domain that satisfies the expression. And that subset is called the solution set. Okay, so values for the variable that are in the solution set are referred to as solutions or roots of the expression. Okay, so values in solution set are solutions or roots. Okay. So let's go back to our example a greater than 11, and let's see what our solution set would be under these different domains that we specified. Well, when a is in 10, 15, 20, 25, then our solution set is a is in 15, 20, 25, right? All of those values for a would satisfy a is greater than 11. 10 is the only value that doesn't satisfy it. Okay, Now when a is an integer, then the values for a that satisfy the expression would be 12, 13, 14, etc., right? All the positive integers that are greater than 11. Similarly, when a is in the domain positive integers, we'll have the same solution set. And finally, when a is in the domain 0, then our solution set is going to be, our solution set is going to be the empty set. Right? This can be expressed with curly braces that don't have anything inside of them, or it can also be this 0 with a line through it. That also means the empty set. So now that we've seen this example, I think we want to revise our statement about once the domain is specified, there will be a subset of the domain that satisfies the expression. Maybe we want to say there may be a subset of the domain that satisfies the expression, because maybe we wind up with just the empty set as our solution set. Okay, so let's do a couple of examples here. In the first example, we want to solve x minus 5 equals 6, where x is restricted to the domain 10, 11, 12, 13, 14. Now, one rather tedious way of solving this would be to say, I have all these possible values for x. I'm just going to plug in each of these values and see if my statement is true, right? So I could say, well, 10 minus 5 equals 6. No, it doesn't, so that's false. 11 minus 5 equals 6. Ooh, yes, it does. But now I have, 12, 13, and 14 still in my domain, and I would have to check those. 12 minus 5 equals 6. No. And down the line. A much less tedious way of solving this would be to say, well, I'd like to isolate x so that I wind up with this expression x equals something. And in order to isolate x, I need to get rid of this -5 on the left-hand side. The way that I do that is just add 5 to both sides, right? So I have x minus 5 plus 5 equals 6 plus 5. I haven't changed my equality because I added 5 to both sides. Now these guys go to 0. This goes to 11, and I wind up with my x equals 11. So my solution set is x in the set 11. Okay, so that was one example. Let's do another example. Now, we want to solve 3n equals 7, where n is in the domain positive integers. Remember that z is integer, and when I put this little plus, I mean positive integers. Okay? So if I first ignore the domain, don't even think about it, then I might say, well, in order for this equality to be satisfied,
then n needs to be 7/3. Okay? When I look back at my domain though, I say, well, 7/3 is not in the domain of n. N cannot be a fraction. Right? It has to be an integer. So there's no value for n over the domain positive integers where 3 times n can be 7. Therefore, my solution set is empty. Okay, let's do another example. Now we want to solve x plus 8 greater than 9, where the domain of x is all real numbers, and we want to graph the solution set. Okay, so here we again want to wind up with x by itself, x greater than something, right? But we've got this pesky 8 on the same side as the x. So we happily say x plus 8 minus 8. We need to do the same thing to the right-hand side, minus 8. This goes to 0. This goes to 1. And now we have the solution set as x such that x is greater than 1. Okay, so the way to read this, where you have the x and the colon, is x such that x is greater than 1. And sometimes you'll see even more shorthand, which is like x such that x greater than 1, right? Where this st is just such that. All right, so now we have x greater than 1, and that's the thing that we want to graph. So we have our number line, 0, 1, 2, 3. Well, x is greater than 1, and it's everything that's greater than 1. So we need a circle, an open circle on that 1. And then we just indicate with a line and an arrow that, hey, it's going to be everything that's bigger than that. Okay. Let's do some example exercises now. So this is coming from the oral exercises. We're going to take a look at number 10. So number 10 is saying, I want to solve this expression for x greater than x plus 8, where my domain of x is 0, 1, 2, 3, 4, 5. Okay. Again, I want to have x on just one side. But I also want to make a note that here I just have these 6 values. So, you know, really, I could just enumerate the possibilities, right? I could say, well, is this satisfied for 0? No, it's clearly not. Is this satisfied for 1? No, it's definitely not. For 2, absolutely not, right? 4 times 2 is 8, and I've already got 8 on the right-hand side, so that won't work. What about 3? Well, 4 times 3 is 12 over here, and then 3 plus 8, well, that's 11. So that does work. And then if I looked at 4, well, that's 16 greater than 12. Indeed, that's true. If I looked at 5, well, that's 20 greater than 13. That's also true, right? That was the tedious way of doing it. The not so tedious way is saying, hey, I want to bring this x over to this side so all my x's can be together. When I do that, I wind up with 3x greater than 8. Okay, now I really want x all by itself. So that's equivalent to the expression x greater than 8/3. Well, what is 8/3 exactly? Eight-thirds is 2.666, repeating. So anything that's, 3 and beyond is going to work, right? And that's what we already found over here. Okay, so final answer, the solution set is x such that, maybe we don't do it that way because it's not really in terms of x. X in 3, 4, and 5 is our solution set. Okay, let's do another example. This is going to be oral exercise 23. So 23 asks us to solve 3 less than z less than 3, where z is a positive integer. Remember that this funky looking z is for integer, and when I put this plus, I mean positive integer. Okay. The only integer that could even be sandwiched between two 3's is a 3 itself, right? So, if I add 3 less than or equal to z less than or equal to 3, then this expression would be satisfied with z equals 3. Here, in the original expression, I don't have any less than or equal to symbols, right? I just have less than. So z being greater than 3, fine. But then z also needs to be less than 3. That's not so fine. There's no integer that can satisfy this, right? If I substituted in 3 for this original expression, then I'd have 3 less than 3, also less than 3, but that's not true because 3 equals 3. So, final answer, solution set, is the empty set. Remember that can be written with these open curly braces, or it can also be written as this 0 with a line through it for the empty set. Okay, let's do a few more examples. So now these are going to be the written exercises. We're on to the written exercises now. Let's take a look at number 10. So number 10 asks us to solve the open sentence. So we want to solve this expression 18 minus 2n equals 16, where n is an element of 0, 1, 2, up to 8. Okay. So we would like this n to be all by itself, right? So we can bring this 16 over here. We can bring the 2n over here. When we do that, we get 2 equals 2n, which means that n equals to 1. If I divide both sides by 2, I get n equals 1. So that means n is an element of the set 1, or I could write it as n such that n equals 1. Okay, let's do another example. Let's take a look at written exercise number 14. So here we want to solve n squared greater than n such that, remember when I put these st, I mean such that n is an element of that same set as before, 0, 1, 2, up to 8. Okay, well, what we would really like to do is isolate n again, right? Here we have a little bit of a problem in that we have the n squared here and the n over here, and the way that we would want to isolate n is by dividing both sides by n, right? Because then we would get n is greater than 1. Now, ordinarily that's something where you really have to think about the domain of n, right? Because if n were negative, then the inequality would change, right? It would go from a greater than to a less than. Now, if n is 0 and 0 satisfies our original inequality expression, then we can't just divide by 0 because division by 0 is not allowed. Well, so the thing that we want to do is we take a look at our domain. We say, well, it's okay if I divide because I don't have any negatives in my domain, so I don't have to worry about the inequality flipping. And I don't have to worry about division by 0 because 0, if I plug in 0, well, 0 squared greater than 0, it's the same as 0 greater than 0. That expression is false. So I know that 0 is not going to be in my solution set, so I don't need to worry about it. That means I can just do my division and wind up with this n greater than 1. So my solution set is going to be n such that, remember when I write this colon like this, it means such that n is greater than 1. So that's my solution set. It's kind of my solution set because really I'm only allowed to go up to 8. So instead, I'm going to say my solution set is
n is an element of 2, 3, 4, 5, 6, 7, 8. That's my real answer, which I'm going to box to indicate that that's the answer that I have. Let's do another example. Now we're going to take a look at number 22. So number 22 asks us to solve 7 greater than or equal to y greater than or equal to 2. And now our domain for y is the positive real numbers. Okay, so real numbers has this r, and I'm going to indicate positive with this little plus sign here. So this means positive real numbers. And it asks me to graph the solution set. So we know that y is going to be between 2 and 7, and it's really just everything between 2 and 7, including 2 and 7. And we know that it's everything because everything that is between 2 and 7 satisfies our domain of y being a real positive number. Okay, so we can just write our solution set as y such that 2 is less than or equal to y, which is less than or equal to 7. That really is just the solution set, right? And when we graph this, I've got 2 over here, 3, 4, 5, 6, 7 over here, and it's going to be, because of the greater than or equal to sign and the less than or equal to sign, or from the perspective of y, I'm going to include the 2 and the 7, and then I'm going to take everything in between, which I'm going to indicate with this line here. Okay, let's do another example. Let's take a look at number 37. So number 37 asks that it's the same instructions as before. So we're gonna solve y plus 2 greater than or equal to y, where y is not a positive integer, but a positive real number. Okay. So if I start thinking about the positive real numbers, well, at the boundary of that is going to be 0, right? Everything which is greater than 0 is going to be considered a positive real number. If I took a look at 0 as a possibility for this expression, just to see what's on my boundary, then I would have 0 plus 2 greater than or equal to 0, which would be 2 greater than or equal to 0, which satisfies my expression, right? If I
look at this expression and tried to isolate y, right? Tried to get y by itself. Well, I would subtract y from both sides, and I would wind up with 2 is greater than or equal to 0, which is always going to be the case, right? 2 is just bigger than or equal to 0. That's just how it is. So that tells me that my solution set is going to be all real numbers, all positive real numbers, because my domain is the positive real numbers, and everything in my domain is going to be able to satisfy y plus 2 greater than or equal to y, right? Another cool way of thinking about this is, well, when I add two positive numbers, I'm going to wind up with a bigger positive number. So when I add y, which is a positive number, with 2, which is another positive number, I'm always going to get something that's bigger than the y that I started with. I'm also always going to get something that's bigger than the 2 that I started with. So that's kind of cool. Now when I graph my solution set, it's going to be all positive real numbers. So here's 0, minus 1, 1, 2, 3. And the graph for this just looks like open circle on 0 and a line in the positive direction with an arrow indicating I just go on forever. Okay, let's do another example, which is going to be number 47. So number 47 asks us to take a look at the expression 3a plus b greater than 7, where the domain of a, that's not written very well, the domain of a is 1, 2, and the domain of b is 3, 4. And what we want to do is replace a and b with all possible pairs of values from their domain, from their respective domains, and just identify whether the expression is true or false. Okay? So first we're going to enumerate the possible values, the possible pairs of values for a and b from their respective domains. Okay? Let's see what that looks like. So I've got a, I've got b, and then I'm going to have my expression 3a plus b greater than 7, which I'll evaluate, and then I'm going to make a statement of whether this is true or false. Okay? So a can be 1 and b can be 3. A can be 1 and b can be 4. A could be 2 and b could be 3. Or a could be 2 and b could be 4. So those are going to be my inputs. And now I'm going to evaluate the expression for each of those. So I've got, for this first one here, I've got 3 times 1 plus 3, which is going to be 6 greater than 7, question mark? No, that's false. Now I'll take a look at this. So 3 times 1 plus 4, that's 7 greater than 7? Well, that's not true either, right? This would be true if instead of that greater than sign, I had the greater than or equal to sign. But I don't, so it's false. Okay, now I'm going to take a look at this. So this is going to be 3 times 2 plus 3, which is going to be 9, greater than 7? Yes, that is true. Now I've got this one, which is going to be 3 times 2 plus 4, which is 10, greater than 7? Yes, it is. All right. And that's it. We are done with that problem. Let's do one final problem, one last example problem, which is going to be number 53 from your book. And number 53 asks us to write 2 open sentences for which the solution set over the real numbers is the given set. And in our case, the given set is all real numbers except 0. Okay, so I want to write 2 open sentences where my solution set over the domain real numbers is all real numbers except 0. Well, the simplest one is just x doesn't equal 0, right? I don't want x to be 0. I'm just going to say x doesn't equal 0. My domain is x is a real number, and my solution set is the one that we're looking for. It's that star. Okay? Another open sentence might be x is greater than 0 or x is less than 0, right? For x is a real number, I still get the same solution set that I was looking for. Now, another cool one, or another one that I think is cool, is I know that I want to put something in, and like, how do I say it? I want to put something in as x and wind up with something that's different from 0. And this needs to be done for both positive and negative values. So, you know, it would be nice if somehow I could wind up with just one inequality sign, which is valid for any positive or negative value of x that I put in that's in this solution set. So I could say x squared is greater than 0. With my domain, again, x is a real number, and again, I get the solution set as star. Now this one's really cool because I can just do it with one inequality, right? If I put in anything other than 0, this expression is satisfied. So that's why it has, you know, this same solution set. Okay, and then I'm going to box my answer. Okay, so that's it for the examples. Now, the problems that I think would be a good idea to do are from the oral exercises, number 6 and 21, and from the written exercises, number 12, 15, 29, 32, 40, 48, and 51. All right, that's it for